Try to pull a heavy metal cable perfectly straight between two towers. The mechanical tension required to fight gravity is so extreme that the line will snap under its own stress. But let that same cable hang entirely loose, and the live wire will droop straight down and strike the earth. To keep the power grid standing, engineers have to find an intentional middle ground. They call this sag, the calculated dip that balances the horizontal tension of pulling the wire against the vertical downward pull of gravity. This diagram shows a suspended wire's natural catenary curve, governed by a complex hyperbolic equation. Because calculating this globally is inefficient, engineers approximate it as a simple parabola when sag is under 10%. Here, the lowest point hangs perfectly in the middle. That mathematically pure symmetry works beautifully on a whiteboard. Out in the actual world, the ground is rarely flat, rendering this simple baseline practically useless in the field. Consider a standard geographical obstacle, spanning a 300-meter river. On one bank, the support tower sits 30 meters above the water. Opposite, a steep hill puts the second tower at 90 meters. As you can see in this plot, the moment the supports are at unequal heights, our standard parabola distorts. To track the new deepest part of the dip, we use this specific distance formula. Notice how the true lowest point of the curve shifts sharply away from the center and towards the shorter tower. If we run the actual numbers, using 2,000 kilograms of working tension and a conductor weighing 1 kilogram per meter, the equation outputs a horizontal distance of -250 meters. That negative distance introduces a condition called uplift. The lowest point of this mathematical curve doesn't actually exist between the two towers. It sits 250 meters completely outside the physical span, effectively pulling upward on the shorter tower. Engineers map this invisible, virtual lowest point because they need it as a rigid mathematical anchor. Measuring back from that negative position, they can accurately verify that the midpoint of the wire hangs exactly 54.375 meters above the river. Tracking that lowest point mathematically prevents thousands of pounds of electrified metal from dragging through the water or clipping a hillside when navigating extreme terrain. Out in the open atmosphere, the physical weight of the wire is constantly changing. In freezing conditions, a heavy layer of ice builds up entirely around the conductor. This adds direct vertical dead weight, pulling the cable further down toward the ground. Simultaneously, a winter storm brings heavy winds. Wind acts as a contradictory force, pressing horizontally against the newly expanded icy surface of the wire. This diagram shows the cross-section of the total force. We have a downward vertical load from the ice and a horizontal push from the wind. Engineers calculate the effective weight by using the Pythagorean theorem, drawing a diagonal line to find the combined vector force. This combined force results in slant sag. The extra weight pulls the wire down, while the wind blows it sideways, forcing the entire suspended parabola to swing diagonally through three-dimensional space. If a grid designer ignores those specific weather vectors, that sideways swing blows the live wire out of its designated right-of-way and into nearby trees or structures. The static equations have to absorb this dynamic atmospheric chaos to remain safe. Apply these calculations on a macro scale. There are millions of miles of transmission lines spanning the globe, and every single span is mathematically optimized for its exact location. Maintaining strict physical clearances is a legal mandate imposed by governments to prevent civilian casualties and property destruction. We can see this directly in the Indian electricity rules. A transmission line operating between 66 and 110 kilovolts is legally required to maintain exactly 6.3 meters of clearance from the ground at all times. Miscalculate the catenary constant, or fail to account for the horizontal push of a winter storm, and the line dips below that legal threshold. The result is an immediate risk of a localized casualty or a cascading grid collapse. Power lines are heavy metal strung in constant mechanical tension. They function as living mathematical equations, continuously balancing unseen forces to keep modern civilization running securely. Look at a massive power grid at night. The sheer physical scale of the steel towers and heavy lines stretching across the landscape is staggering. You might assume that if you completely disconnect a transmission line at the receiving end, the flow of electricity simply stops. But even on an open circuit, a massive amount of current continues to flow through the wires. Engineers call this the charging current. The extreme high voltage of the system physically pushes electricity against the structural boundaries of the line itself. The entire transmission line is effectively functioning as a giant capacitor. Across hundreds of miles of cable, electrical charge builds up strictly on the outer skin of the metal, utilizing the empty air between the lines as a medium to store reactive power. Accounting for this invisible stored charge is a vital safety requirement. Without precise calculations, this surplus reactive power can push line voltages beyond their intended limits, creating a constant pressure that engineers must carefully balance to keep the grid stable. To calculate how much power a system can hold, let's strip away the grid's complexity and look at a theoretical single-phase system, just two parallel wires suspended in a void. Field lines stretch between conductors, turning air into an energy storage bank. Capacitance equals the permittivity of free space, divided by the natural logarithm of distance over radius. Inside the conductor, the electric field is zero. Charge is trapped entirely in that absolute outer skin. This behaves completely differently than magnetic inductance, where flux penetrates straight through the solid core of the wire. For capacitance, the internal metal doesn't matter at all. The mathematics of capacitance are dictated entirely by surface geometry and the vast empty space separating the metals. Look closely at this real-world lattice tower. Standard three-phase grids carry 3 active wires, and the support arms suspend them at physically unequal distances. This asymmetric spacing breaks our basic math. It creates unequal capacitance between the wires, generating an unbalanced reactive power across the phases. The solution is transposition. Engineers physically rotate the wires to average out unequal distances. The mathematical counterpart is the geometric mean distance. Taking the cube root of these 3 asymmetric lengths generates a single equivalent distance, which substitutes back into our formula for 3-phase grids. The massive physical rotation of cables along a highway is a direct, hard-coded requirement to satisfy the logarithmic math of balanced power delivery. So far, we've modeled these wires in a mathematical void, but in reality, they hang directly over the Earth, which functions as an infinite conducting plane. The ground interrupts the electric field. To calculate this, we used the method of images, imagining a ghostly mirrored wire buried underground with an opposite charge. This image pulls on the real wire, increasing capacitance. But as tower height increases, this grounding effect weakens. Tower height serves 2 purposes. It provides physical clearance for the world below, and it functions as a mathematical lever used to minimize the Earth's capacitive interference. Look at the intense geometry of this V-shaped structure. At major junctions, bundled conductors and multiple circuits stack all these geometric rules together. Every variable is a strict engineering trade-off. Increasing the thickness of a wire lowers its electrical resistance, but it simultaneously increases the surface area, which drives up the capacitance. Spreading the wires further apart prevents dangerous arcing and simultaneously drives the capacitance down. Conductor radius, phase distance, and tower height. These 3 variables act as the master dials to govern the charging current across the system. Transmission line engineers are meticulously sculpting the empty space between the metals, mathematically balancing geometry to safely store the invisible power of the modern world. Look at a high-voltage transmission line suspended across the landscape. From the ground, these heavy metal cables appear perfectly still, inert pathways passively carrying electricity from a power plant to your city. But the electricity flowing overhead is alternating current. The electrons inside aren't flowing in a smooth, continuous river. They are violently oscillating, reversing their direction dozens of times every single second. Every time that current surges, it generates a magnetic field. Because the current constantly reverses, the magnetic field is locked in an endless cycle of expanding outward and then collapsing back into the wire. The grid is an active magnetic battleground. The electrical energy pulsing through the cables is constantly fighting against its own physical properties. In the 1830s, physicists like Michael Faraday realized that whenever a magnetic field changes, it induces a new voltage, an electromotive force inside the conductor. Heinrich Lenz quickly identified the catch. that newly induced force pushes back. It flows in the exact opposite direction of the original current that created it, acting as a direct physical friction against the flow of power. Engineers call this pushback inductance. It is the grid's inherent, invisible resistance. Because this induced force constantly pushes back, it creates a timing delay. The current can no longer keep pace with the voltage, forcing the electrical phases to lag. If this lag isn't perfectly calculated and balanced across hundreds of miles, the synchronization required to keep the grid alive vanishes. Preventing a total system failure requires translating these massive, invisible forces into precise, controllable mathematics. To calculate that friction, we have to look inside the metal itself, where the magnetic field doesn't just exist on the outside. There are magnetic loops physically trapped inside the solid metal of the conductor. We call this internal flux. You might assume a thicker wire traps more magnetic force, but the math reveals a specific property. Assuming the current density is uniform, internal inductance is a fixed constant. It stays at 0.05 millihenries per kilometer, regardless of the cable's thickness. Meanwhile, the external flux, the magnetic field radiating outward from the surface of the wire into the surrounding air, varies depending on the distance to any neighboring wires. Running separate mathematical equations for fixed internal flux and variable external flux across thousands of miles of cabling is an agonizingly complex process for grid modeling. To bypass this complexity, electrical engineers created an elegant mathematical cheat code, the geometric mean radius, or GMR. Look at what happens to the wire in this diagram. Engineers take the physical radius of the solid cable and mathematically shrink it by exactly 22.12%. This creates a fictitious, totally hollow wire. By substituting this slightly smaller hollow radius into their models, the internal flex is perfectly accounted for. The math completely bypasses the inside of the wire, collapsing two messy equations into one clean, unified formula for total inductance. By adopting this specific mathematical geometry, engineers can treat a solid wire as a hollow shell. It turns the chaotic internal physics of a power line into a single, predictable variable that keeps the system steady. Of course, a power grid requires a complete circuit. We need to introduce a return wire. In this diagram, we see two parallel wires. Because their magnetic fields overlap and interfere with one another, we have to measure the physical space between them. This distance is called the geometric mean distance, or GMD. Our unified equation now relies on a ratio. The total inductance of the line is driven by the distance between the wires, the GMD, divided by the effective size of the wires, the GMR. To keep inductance low, engineers want the denominator, the GMR, to be as large as possible. They achieve this by taking a single solid wire and splitting it into a bundle of smaller, spaced-out strands. This artificially expands the effective footprint of the wire, forcing the total inductance value down. Engineers intentionally manipulate the physical layout of the metal to hack the mathematical ratio, suppressing that invisible friction so power can flow freely. That elegant math gets complicated quickly when we scale up to a massive three-phase transmission line. In a perfect mathematical model, the three phases are arranged in an equilateral triangle with identical distances between wires. But in physical reality, towers hold wires asymmetrically, either horizontally or vertically, meaning the distances between phases are unequal. This unequal physical spacing means the magnetic fields overlap unevenly. The flux linkages vary for every single wire, resulting in different amounts of inductance across the phases, which creates an unbalanced grid. Since we can't change the laws of physics, and it's too expensive to build perfectly triangular towers across the globe, engineers have to solve this math problem using geography. The solution is a massive brute force technique called line transposition. Every few miles along a transmission route, the giant metal cables are physically twisted, swapping positions on the tower structure. The rotation follows a strict logic. By shifting positions, each phase spends the exact same amount of distance in every physical location over the total length of the line. By the time the power reaches its destination, the geographical swapping has completely normalized the average inductance for all three phases. The messy physical reality is forced to perfectly match the balanced mathematics. The modern world relies on this precise balance. Keeping the grid humming is a relentless, ongoing marriage between the invisible mathematics of magnetic fields and towering, brute force physical engineering.
Modern electrical transmission grids rely on massive steel towers to carry hundreds of thousands of volts across vast distances. Because these towers are rooted in the earth, they are permanently grounded. Any direct path between the live conductor and the steel would trigger a massive high-voltage arc discharge. To prevent this, the connection between the wire and the tower relies on an insulator. This component must be strong enough to hold the weight of the cable, but resistant enough to keep the current from leaking into the ground. For lines up to 33 kilovolts, a single solid pin-type insulator is sufficient. The conductor is tied into a groove at the top, using the ceramic body to isolate it from the crossarm. However, scaling this design for higher voltages is impractical. To block 132 kilovolts or more, a pin insulator would have to be so large and heavy that it would become too expensive to manufacture and too bulky for a standard tower to support. Instead of making the insulators bigger, engineers moved to a modular design, the suspension string. This setup uses a series of individual porcelain or glass discs linked by metal pins to form a flexible chain hanging from the tower's arm. This modularity allows for easy maintenance. If one disc breaks, you only replace that unit. More importantly, you can handle higher voltages simply by adding more discs to the string. But linking these discs creates a specific electrical imbalance. The voltage stress doesn't distribute itself evenly across the chain, meaning the unit closest to the live wire is forced to handle significantly more potential than the units at the top. Achieving a uniform distribution across the entire string, a metric known as string efficiency, is the primary requirement for ensuring that no single disc is pushed past its breaking point. When an insulator fails, it typically happens in one of two ways. It can flash over, where electricity arcs through the air surrounding the unit. Or it can puncture, where the current burns a permanent path through the insulator material itself, destroying the disc. The risk of puncture is tied to the physical structure of the string. Each disc is essentially a non-conductive material sandwiched between two metallic fittings. This arrangement creates mutual capacitance. Each disc acts as a capacitor, passing charge down the string. Ideally, current is identical at every link. The voltage drops equally, with each unit in a 3-disc string handling exactly 1/3 of the load. But this ideal state only exists on paper. In the real world, the proximity of the grounded metal tower changes the electrical behavior of the entire string. A second type of capacitance forms in the gap between the metal links and the tower. This is shunt capacitance. These act like small leaks, drawing charging current away from the string and into the tower at every junction. Because of these leaks, the current is not the same at every disc. The unit at the very top, closest to the tower arm, carries the least amount of current and experiences the lowest voltage stress. As you move down the chain, current accumulates. The disc nearest the conductor carries the string's full current, plus the leakage from every node above it, resulting in the highest electrical stress in the entire assembly. If this stress exceeds the material's dielectric strength, the bottom disc will puncture. Once that unit fails, the remaining discs take the full line voltage, often leading to a total failure of the insulator string. To maintain high string efficiency, engineers must find ways to equalize the voltage across these discs. One method is to increase the length of the tower's crossarms. By moving the string further away from the steel structure, you reduce the shunt capacitance, but the increased cost and weight of the tower make this an expensive fix. Another option is capacitance grading, using larger discs with higher capacitance at the bottom of the string. While effective, this complicates manufacturing and makes repairs more difficult, as every disc is no longer identical. The standard solution is the guard ring. Connected directly to the live conductor, it surrounds the bottom unit. The ring introduces capacitance that feeds current back into the junctions. This cancels leakage to the tower, ensuring the current through each disc remains nearly identical. By mathematically canceling out these parasitic leaks, engineers turn a vulnerable chain of discs into a reliable barrier, keeping the grid's highest potentials safely suspended above the ground.